All right, so we have been dealing with mass transport and fun notation that comes along with it. So one of the last things we've done is basically look into the equations of change for single species that we don't denote with alpha. And what we got to is that basically d rho alpha being the density specifically for that chemical species. So just take a mass of all of it and divide by volume. D rho alpha dt, it has contributions from diffusion. Okay, so what walks into the this volume element just due to diffusion. Then convection, what's carried into the volume element, and production if we do actually have any chemical reactions. Now, one thing that we, of course, are wondering, what happens if I sum all of these contributions up? Technically, I should be getting a continuity equation for that phase that we, whose density we denote with rho. So if we quickly do that, so basically I take a sum of all these. Okay. Then this will become, it's going to be sum of d rho alpha dt, which is the same as d dt of the sum, right? And that sum is actually rho, right? So this becomes and that is d rho dt. Okay. Now this sum of divergence of all j, is the same as divergence of the sum of j. And since all of these fluxes are defined relatively to the movement on the phase, sum of all of them is 0. So if I had just two, JA plus JB would be 0. So this is simply by definition of these fluxes. And then we have some divergence of the sum of all of the rho alpha, which is basically divergence of the sum rho alpha v, divergence all of this. Plus sum of R alpha. Good news is I haven't written A a single time. By the time I get trained on alpha, we're going to switch back to A. So this again, this here is rho, and this here is sum of all of the production terms. So this is mass rate of production for all of the species. Sum of all of it has to be 0. So indeed, this term disappears, this term disappears. I do get my d rho dt is minus divergence of rho v. That's what I should get. So this is my equation continuity for the whole thing, for the mixture. So now we're just going to briefly look at the basically various variations. How do I write this so that we can use this in a calculation? So let's just quickly look at the molar. Oh, welcome. I haven't had this in a long while. So molar quantity equivalence. So one thing that is always useful to have in mind is that my mass density and molar density are simply related by molar mass of the component. Okay? So this is molar mass of component I, alpha. And the same is true for fluxes. So my N alpha is M alpha N alpha. So this was my mass flux, combined one. And the uppercase we use for molar version of it. So basically, if I take my equation of continuity for a single species, and I simply divide it by molar mass alpha, okay? So if I have d rho alpha dt and alpha plus r, and it's too warm today for anybody to have gloves. Yes.
Alpha means the molar mass of the alpha, right?
Species alpha, yeah.
Isn't C molar concentration?
Yeah. So mass concentration and molar concentration.
Okay, but you put a rho there.
The arrow is to the end, alpha.
The C.
How's that?
If you want, try with this.
Let's try.
I forget to get up.
I'm riding a motorcycle this morning.
Yeah.
Woohoo! Awesome. I don't know that it's easier, but okay.
fine.
A little too thick. All right. Thank you. Yeah, they're very thick. Okay. They're not doing anything. Yeah.
Why?
Okay. All right. So if I divide this by m alpha, okay, what I'm gonna get is my molar equivalent. It's forcing me to also press harder. So if I divide n alpha by m alpha, again, molar mass is something that is constant. That's not going to change. So I can just divide with it easily. And I'm also going to do R alpha is m alpha and molar rate of production. And since this is, just to write it down, so this, by the way, just to give you some hint where we are, I did post notes, but this is 19.1.10 in the textbook if you need to kind of go, because there will be a lot of these equations, so just to give you some anchor. And that is in the notes, I posted it as well. So this is C alpha V star. And this is my uppercase J alpha star. So this is again molar flux, molar version of the flux, plus R alpha. So if I was summing this just like I did for the equation of continuity, what we would get is sum of all C alphas is C. So I'm going to immediately get C here. So if I do sum of alpha, I don't know that I could have written that smaller. So if I sum over all alphas, then I'm going to get, similarly as before, C V star. And V star is that average using X alphas as opposed to omega alphas. So if I go and average velocities, I take weights that are basically X alpha. And plus, these are, so J alphas will disappear when I sum them up, because by definition their sum is 0, but R alphas will not. So mass is conserved, but number of moles is not conserved. Okay. So that stays as a sum. Okay. So common way to also express this equation of continuity. So this is just molar quantity equivalence. And we're going to interchangeably keep writing both. How about I keep black color for the regular one and blue for the molar, just to have some, to keep some track. So basically, there's another way to express this one. That is more common for computation. Typically, we actually go and compute omega alpha, not necessarily rho alpha. So this is the same as, and I could also break down what n alpha is. So common way to write this is that this is rho times d omega alpha dt. Remember that rho alpha is rho omega alpha. Plus v dot, whoops, how did I do that? So basically, I wrote n alpha for what it is, so it has a convective component. And it's not necessarily super straightforward, but basically there is some of that, I need to kind of write details and employ equation of continuity within. And this is your 19.114. Just to give you some anchor to the stuff in the textbook. Yes?
The velocity
In this one, no, these are omegas. This is not in blue. So yes, if we're writing in blue.
Can you explain again how to compute?
So basically, this N alpha, it has both J alpha and the convective component that has V and rho alpha inside. So basically, you write down what that is and then send the convective component on the left-hand side. But there has to be a little bit of breaking down of the divergence term to get this particular form. And I left the notes if you want the details. And the similar thing in molar version would be C plus, and this one has V star dot X alpha and there's this. Now I'm going to introduce beta. Watch for it. This is beta. So these are sort of your most common versions because most commonly we compute X alpha and omega alpha.
Where the last one comes from?
Mhm.
Where the last term comes from?
The last term?
Yeah.
Again, from breaking down and the fact that this sum doesn't go to 0. So you would have had that sum in the top equation as well, sum of R alphas, except that one is 0, so it disappears. So when you do the summation.
And why you change the subscript?
Because I'm multiplying it with X alpha, so I'm not going to use the same alpha for the summation next to it. I could, but that would be very confusing. So this is X alpha multiplying the entire sum. Now, in practice, again, this is just a general formula. In practice, we're going to use binary mixtures. So it's going to be A and B really only. So the sum is going to be RA plus RB, right? It's not going to be all that complicated. And another thing that we're going to do is, but we're going to start doing that once we actually start solving problems. So I can use basically a version of Fick's law for expressing J alpha. Okay? And I'm going to break down this formula writing. Let's actually solve some problems. So these are just general equations of change. Okay? So we're going to now introduce a problem, and I'm going to solve it basically using both equations of change and shell balance just to see the difference. So this is example 18.2 in the textbook. Diffusion through a stagnant gas film. This is one of the most common introductory examples. I have a beaker. On the bottom of it, I have liquid A. And on top of it, I have some gas B. This line is Z equal to Z1. This line is Z equal to Z2. And I have, since the bottom is liquid, I have vapor of that liquid diffusing through upwards. Okay? So basically, I have a shift in my writing. I can't, my precision is affected. Oh well. So vapor of A diffuses through. Now here I have XA is equal to XA1. So this is my molar fraction of A. And I am counting either that this is not going on for a long time, or there's some sort of constant supply of liquid A, so that surface of A is not moving from Z1. Okay? So this is assumed static, assumed put. Let's say that this is surface of a lake. There's plenty of rivers or whatever that supply that lake stays. And that means if we are in Austin, it's around this time and not in July. Okay. So, there are no rivers in July. All dried up. All right. And then I'm also at the top maintaining XA is XA2 by some artificial means, for instance, by gas constantly blowing. I have blow dryer of some sort, or a wind, or something like that, that maintains constant XA2. And this gas concentration at the interface, that's basically corresponding to the equilibrium of vapor and liquid interface. So corresponds to vapor, liquid equilibrium. So basically it is partial pressure of the vapor phase divided by pressure, if I ever need to compute what it actually is.
Say that first word again.
Corresponds to vapor-liquid equilibrium. And the way to compute it is to take partial pressure of vapor, A, divided by overall pressure. And needless to say, we assume these vapor of A and B to be ideal gases. So let's say we want to solve for concentration of A in this B region. Okay? And we of course assume only one-dimensional case, so only Z is important. So we can have shell balance approach, or we can have just use the formulas that I gave you. So let's start with the shell balance, okay? And then we're going to actually solve it with the formulas. No news here. It's actually going to be easier to integrate and find the solution when you do shell balance, because you kind of go step by step. Whereas the other formula just gives you second order equation that you need to solve. Differential equation second order that you kind of have to look at and say, what do I do with this, okay? So in that sense, shell balances are sometimes preferred, okay? Now, my shell balance here is, of course, rate of mass in any kind of slab, which is my z direction slab between z and z plus delta z, okay? So rate of mass of A coming in has to minus what's coming out. So my shell balance is rate of mass of A coming in minus rate of mass of A coming out plus any production is 0. So I'm going to quantify this with my combined mass flux of A, and it's that NA, either uppercase or lowercase. And in this case, I'm already giving boundary condition in terms of X, therefore I have to choose the molar quantities, right? Because that's how my boundary conditions are given. So if I take my S as my cross-sectional area into this plane that I don't see, then basically if I have Z sort of somewhere here, Z, and then Z plus delta Z, okay, what's coming in at Z, okay, is the Z component of NA evaluated at Z times the surface area, right? So if my S is my surface area, then I have S N A Z evaluated at Z. So again, uppercase N is my combined molar flux of species A. So it has both the diffusive and convective component. Minus S N A Z evaluated at Z plus delta Z. And I don't have any production, so that's it. I assume no reactions are going on. So when my standard procedure, divide by S and delta Z and take limit when delta Z goes to 0. So this is going to be minus N A Z Z Z plus delta Z divided by delta Z, and I take a limit when delta Z goes to 0. I get a simple equation, deceptively simple. So this is all nice, except that I'm never solving for NA. It's a very simple equation in terms of NA. But that's not what my boundary conditions are, so that's not what I'm solving for. I might want to know it at the end, but I can't solve for it because I don't have boundary conditions for this. So let's write down what this is by definition. My NA, by definition, is a vector is my JA plus CA V star. So my diffusion, molecular diffusion plus convection. Yes. Though for uppercase J, I'm not that confused what it is. For V, I have to put a star. J, if I drop it, as long as you see that it's uppercase, then it's fine. But I'm going to put stars because my handwriting is what it is. So for Z component, I have JAZ plus CAVZ star. Now, for JA, okay, this is where I can do Fick's law. Okay. So this is going to be minus CDAB of DXADZ. And here, I assumed that CDAB is approximately constant. So if I take any derivatives of it, just keep that in mind later, it can just easily come out of the derivative. And then let's just write down what VZ star is. VZ star is XA VAZ plus XB VBZ. Now my C, so this is minus CDAB DXA DZ plus, what is C by definition? CA by definition? CA is CXA. Times XA VAZ So here I can get my C to multiply XA and XB that are in this V star definition. And when I do that, I'm going to have XA left outside, C XA VAZ is CA VAZ, which is NAZ again, and NBZ. So CXA is CA VAZ plus CD VBZ. And this, by definition, is NAZ, and this is NBZ. Now, we are going to assume in this problem that my gas B is stagnant. and that actually NBZ, more importantly, is 0. So my second portion here, this NBZ is going to be 0, which is we're counting ourselves lucky. Otherwise, I have to figure out some way to relate my NBZ to NAZ in order to be able to solve for this, because I have coupled multiple things, okay, and it becomes a problem to solve solve the equation. So right now, we are assuming in this problem, so if I have a reaction though, where I might have species B getting formed and moving counter whatever something is coming to the reactive surface and then a new species is moving away. In that case, I can't count NBZ as 0. Then based on that reaction, I will have to figure out what is NBZ in terms of NAZ that is coming to the surface, for instance. Okay? So in the cases of reactions, we actually can't assume that this is 0. But I have to figure out what it is in terms of NAZ so I can actually go solve, because things are coupled together and I need to solve for them. Okay? So luckily we're going to assume this is 0 for this problem. So ultimately, what this becomes is NAZ is minus C DAB dXA DZ plus XA NAZ. And this is good because I can express NAZ in terms of XA and then plug that into the equation that we have dNAZ dZ is equal to 0, and then solve for XA, which is what I want. So this whole exercise is getting XA somehow in this business of NAZ. Right? So basically, this gives me that 1 minus XA NAZ is minus C DAB dXA dZ. So my NAZ is minus C DAB divided by 1 minus XA dXA dZ. This is essentially what I need to proceed, because I can take derivative with this with respect to Z and solve for XA. Like I didn't know what NAZ was in terms of XA, and my boundary conditions are in terms of XA. So my DDZ of NAZ is DDZ, there's this minus sign of C DAB DZ, and that is equal to 0. Now this is something I can solve given the boundary conditions I have. So this entire half page of exercise was getting NAZ somehow in terms of XA, essentially. Going to the definition and figuring out what it is in terms of XA. Because every time you get a balance, you're going to get it in terms of fluxes, NA, whether it's uppercase or lowercase. Cool. So this is what we're solving. This is where it's actually helpful, that assumption that this is approximately constant, meaning concentration is not changing much, and pressure and temperature are not changing much and are relatively low. Okay? Because in any kind of high pressure, high temperature conditions, or concentration changing a lot or being very large, in those cases you can't assume that diffusivity stays the same. So basically I can just divide by it. So I have ddz of 1 over xa dxa dz is 0, which means that 1 minus 1 minus xa dxa dz is equal to constant. So dxa over 1 minus xa is constant dz. I can integrate this. Separation of variables. So my minus ln of 1 minus xa. Xa is always between 0 and 1, so this is a positive number. I'm good there. Otherwise, I would have to have absolute value or something. Mm-hmm. So I have low concentration and concentration not changing much. So DAB in itself is then assumed constant. But when I'm also multiplying it with C, since C is relatively small and not changing much, I'm assuming that the entire thing is. Molar, so C is CA plus CB. Now in this case, B is not changing, it's just sitting there, right? So overall, the amount of it is not going to change. CA is moving through, right? But as it's kind of moving through, I'm assuming that it's approximately constant. It's not going to change overall sum of it too much. It's just changing its location within the volume. But it's not a huge change. Otherwise, I'm in trouble because I can't divide, and then good luck solving. The flip side of it is like you can't solve. So with that, you approximate this way out of necessity. Okay. So my boundary conditions are given. So at z1, z is equal to z1, xa is xa1. At z is equal to z2, xa is xa2. So I have simple boundary conditions here to put together. So my BCs so this is essentially what we solve for C1 and C2. So that's just an exercise in solving. We're going to write down what that is and then use it next time. And then we're going to also solve this just directly going from the equation just so that you see how that looks like. Okay? But this is essentially problem solved. Quick quiz. What is 1 minus xa1? xb1. So if you want to shorten your writing, you can, but we are solving for xa, so then we're leaving it at